Okay, let me now start officially the lecture. Let me share the presentation which you have in my study. Exactly. Let me, yeah. Again, very shortly, we started trying to define or to speak. No? As I told you, I will try it also to avoid formal definition, in particular formalism in the definition, because again, the course is more topic oriented, and again, and the course for everybody. Remember, simulation is an imitation. Then I try to introduce the concept of the model in order to clarify, in order to tell you without formalisms the concept of system, which is a quite general concept, more general than the concept of process or real world process, because real world processes could be that you have an intuitive idea. System is a little bit more complex, but using the concept of the model or the idea of the model, I tried to explain with words without using formal definitions the concept of the system. Look at here. Model is a simplified and idealized understanding of systems. I don't know if this clarify because I'm using always the same word, the same wording, but this is a little bit the price that we have to pay in order to avoid a formal definition. Very interesting, the correctness. Doesn't a correct model exist? If correct means true, the answer is yes. If correct means valid, excuse me, if correct means true, the answer is no. If correct means valid, the answer is yes. Validity, no? Validation. No? We have seen, we will see more in depth, that validation means something which is useful. No? We are not looking for the true, we are looking for something which could be used, could be useful for us. This is easy to understand that it's not exactly something which is true. Why that? Again, because we try to simplify, we try to idealize a system as in a project, something which we want to describe, but not only to describe. We want to use this. We will see also today with Simulink matter, because if it's extremely complex, probably conceptually can describe better the reality or what we want to describe. But if it's too complex, then it should be extremely difficult to be controlled. It should be extremely difficult to really to work in a quantitative form with software. We are speaking about validation in our wording, but we are not speaking about verification, because verification is connected with the truth. What you're telling you now is just, in this course, just something which is not true. It seems to be strange, but I hope it is valid. Can help. Okay, non-parametric model is a little bit in a contradiction, as I told you, because we will see that in order to build a model, it doesn't matter how, we need to calculate some parameters. We will see also today with MATLAB Simulink or more in depth. Why we are speaking nevertheless about non-parametric model? Even though at the end I have to calculate some parameters, because the distinction consists that the parameter that we are using now in a non-parametric model not necessarily is connected with the physics of the system. Could be that this parameter, they are quite abstract. Therefore, the model which should describe the reality, let me say, of the system, consists of parameter which is there a little bit abstract in the sense. In the sense, non-parametric model means that the parameter and they don't have a physical meaning or a meaning directly connected with the system. Well, let me say with the reality. I mean, it could be that the parameter is not ohms, resistance. They are not money. If I have to do in an economic system, they are not Newton. If you consider in a mechanical system, they are something that physical does not exist. Newton divided money. It is difficult to figure out in a precise meaning. In this sense, parameter, yes, but not directly connected. I will show you now what I intend. Directly connected with the physics of the system, even though this model is useful, should be useful to describe a system. A parametric model is a model in which the parameter, they are directly connected with the physics of the system, with the real system in the sense. Here, do you remember I try to use some nomenclature, descriptive statistic, probabilistic statistics in this course. We will, in this part of the course, I will consider just the descriptive statistics. It is not based on the probabilistic statistic, which I will consider in the next semester in the course a little bit in the course of Kalman filter. I invite you to come to the course of Kalman filter, which is a little bit more advanced. More advanced, I don't want to say, but the Kalman filter is an optimization method, extremely complex, which is really used in the practical application. I don't have time in this course, which is more general, to speak about the Kalman filter. This course is dedicated, even though in complementary to the analysis and the implementation of the Kalman filter. Yeah. Again, it could be nevertheless important in the word, in the nomenclature. Yeah, we are analyze here the descriptive statistic. I mean, is exactly the concept that I will use. I will generate this non-parametric model to describe a phenomenon which consists also of statistical elements without considering directly this probabilistic approach, even though mean value, variance, of course, I will consider also in this session, even though again the probabilistic statistics is more oriented distributions and so on. It's not exactly the approach in this part of the course. You remember this example here to introduce the least square method. I have measurements, these violet points. The question was, now very quickly, the question was, what is the best model curves, the best regressor, the best function, which fit the point. This was the question which I tried to answer last time using an example. Using an example. I mean, assuming that I would like to fit this point using this mathematical model, the polynomial. The polynomial. Do you remember this was an example which I considered from electrotechnics in a motor, X exploration variable. Exploration, recall as that something which I used to explore the phenomenon, the current in X, and in Y, the measurement in flux, in Weber. For current 1, I have, I don't know, more or less 40 Weber, and so on. The question here, in order to introduce the problem, is to calculate for a given family of regressor. This means polynomial regressor. I will answer also the question why polynomial and not trigonometry. I will answer in this session. Probably I will not able directly to show you with MATLAB today, but I hope that to start. Assuming that I give you this, assuming that this model here, assuming that I give you also the order. No, we have to be clear that here I fix the family, this polynomial, and also the order of the polynomial. The problem is to calculate A0, A1, AN parameter, which not always have the physical meaning. Again, on the concept of non-parametric. I mean, here it seems to be just AN. The unit of AN is Weber. because y hat is the function which approximate or that try to approximate in the best way. I will clarify what is the meaning of the best way. The measurements which I have and a finite number of measurements. In this example, I have eight measurements. An is Weber, but here A0 is Weber divided current up to n. This means what is this physically? Therefore, this concept non-parametric in the sense the parameter is there, but it's not directly connected with the physical meaning. If you think about A0 in this expression here, I hope that I share the screen, yeah, because I'm working in another university with Teams. In this sense, it's easy because I don't have to share each window. In this sense, I share the screen. What I see is what I transmit. Here, sometimes I'm speaking and thinking that you see what I am considering, that you don't see it. I don't know if it's clear. A0 is something which Weber divided the current up to n. It's something which is not directly connected with this phenomenon, which is Weber versus current. I mean, it's connected, but in a mathematical sense. Yeah, we will see also today, I hope, at least theoretically, how we can choose the best regressor. Why polynomial and not trigonometric? Why polynomial, not exponential functions? Do you remember I told you a little bit about the basis? I don't want to go in depth on this mathematical aspect. Very important now, because we will go ahead really with this concept here. We think that our representation, in the sense our model, at this moment, the model is, again, y hat. Y hat is the model, is in a function. We can see y hat of x. The measurements are characterized by y without hat. Y1, Y2, Y3, depending of the current x1, x2, and x3, and so on. We think that this representation, which is based on y hat, or in general, the phenomenon, is characterized by two kinds of error, a statistical error and a deterministic one. Again, we will see, based on this concept here, that our phenomenology is based on these two error. We will see how we can choose in the best way the family and the number of coefficients. In our case, the number of coefficients is characterized by the order. But in general, we speak about number of coefficients. I will tell you later. The order states the number of coefficients in our case directly, because, or at least in any regressor, of course, we can find some connections between the number of functions which I am considering and the coefficients. But here, to be more precise, the number of coefficients, A0, A1, AN, the number is equals n plus 1. Very important at the end of this slide, and today we will see together, is the concept of the cost function or the cost functions figure of merit. In order to attack the problem, in which sense? If I say I would like to calculate the best polynomial regressor for a given order n, this means I have to calculate A0, A1, AN, but if I say the best, with respect to what? For instance, I can say that I have been the best professor because I have the best, the larger number of publications. This means the criterion is the number of publications. In accordance with this criterion, we can consider a possible ranking. But of course, come another professor and say, no, this is not a good criterion. We have to consider not only, or absolutely not the number of publications, because we have to consider the quality of the publication. This is a little bit more complex to define a cost function which measures the quality of the publication. But it's not a stupid example, just to say that, uh, of course, the best is with respect to something. It's not the best in absolute. And for instance, in this example, of course, there is a metric there is a method to define the impact of the publication. Is the best, is the good, is the way to measure. Again, why I'm telling you that? Because so the choice of the cost function is something which is questionable. Therefore, the optimization problem is, of course, something which could be valid, and also the choice of the cost function, and we will see exactly today, is a crucial choice, because something which is good for a cost function is not good for another one. The example of the professor is clear. If I think I am the best because it's the maximum number, the people can say, okay, you have the maximum number or the highest number of publication, but your publication is not good. This means it depends on the cost function of the criterion, the sense which we want to consider in order to decide, in order to choose one regressor or one professor with respect to another one. Again, this question we will reconsider at the end of today, or almost at the end. You remember, what is the best approximation? It depends. We will see at the end on this. Now, yes, I slow down a little bit because I received some criticism. I have a regressor, which I gave you at the beginning, exactly this, in the middle, or at the beginning of the mathematical expression. What about this expression? Yeah, here, this sentence say that the measurement y1, Weber, which I received at the current x1, is circa this function calculated at x1. X1 is the value which I have, no? 1 ampere it was. Basically, this sentence here states this situation in which y1 is circa this point. It's not exactly this. Basically, y hat x1 is this point here. But of course, y1 minus this point here, which I don't know where is, because I try to calculate when I will define the cost function. We will see which kind of a cost function. Remember, this least square cost function. The idea is, in an abstract form, this was the criticism which I received from a couple of students, but it's not clear this. No? This point here, I don't know where it is. Because the question is, what is the best position of this point, together of this point, together of this point which I didn't indicate, together with this, together with this, together with this, such that for a given cost function, please pay attention, for a given cost function, I have the best approximation. But again, for a given cost function. You remember last time I told you the possible cost function is to put or to have this each error equals 0. It's not possible. This means I have to meet, let me say, all points. It's not possible. It's allowed. Today I will try to emphasize why this is not what we want, even though it's not possible. Do you remember in high school, you have exactly the example which I have here. No? In the high school, you have 2 points, and we say to the students, design or calculate, calculate the line passing through. We have just 1 line. More interesting is to evaluate, again, we will come back on this question here, what is the difference if I consider this line here, which meet the mean value of these 2 measurements? No? Y1 is here, Y2 is here. Instead of considering this model, instead of consider this line, I consider another line, the line which meets the mean value. It is interesting, because we will see at the end what I want to say. Of course, with 2 points is a little bit an extreme example, but in this case, we can understand that if I meet all points, I fixed the order of the polynomial. We have here 8 points, 8 measurements. This means if I want to meet all points, I need at least the polynomial order 7. I meet all points, all 8. In any case, we have more parameters. Somehow we can see in this sense that we fixed at least a lower bound for the order of the polynomial. And also in this sense, we can understand that I am not free, for instance, to play with the order of the polynomial. It's not exactly the first task, at least not for today, but we will see that the order of the polynomial, the number of coefficients, is extremely important, in the optimization problem. But the problem which I have if I meet all points is that I am considering that the point, the measurements, they speak the truth. This we will see that is not a valid assumption because the measurements are affected by error. This means I include in the model probably too much error, too many errors, and we will come back on this. Yeah, I do this approximation or this expression for all my measurements, M measurement. Typically, the number of measurements, M, is much larger than N. We will see now in a few minutes why. And this expression here can be written in this in another language, the language of matrices, in this form here. Last time we stopped here, I think. I consider a vector of my measurements. The vector consists of M measurements, y1, y2, ym. And the y vector is no, circa, reflect this circa that is everywhere. And what I have here is this exploration matrix. The name is exploration matrix because the matrix consists of the value x1, x2, x3 in accordance with the structure of the regressor. The name is because the x is the exploring variable or exploration variable, which multiply a0, a1, an, which is the vector of our parameters. In this in this case, we can separate clearly what I know with respect to what I don't know. This is an extremely important advantage. Because allows to, let me say, to calculate directly or almost directly the vector theta. Do you remember also in high school? No? If you remember in your high school, when equation, in one equation, if you are able to isolate the unknown on the left part and what I know on the right part, and we can solve we can have the solution. This is quite similar. No? This concept of the separation is extremely important in the context of the solution, or to find a solution. We will come back also a little bit more in depth later, but I would like to say that this concept of the separation is one condition to have a convex optimization problem. Do you remember last time I introduced convex, not convex? It's not the unique condition, but of course, if I can separate, it's clear that is already something which can allow to say if the cost function is in a quadratic one. Remember I told you last time we are in the present. The cost function is in a quadratic is okay, but in a convex one with a regressor structure in which I can separate what I know with respect to what I don't know, the problem is convex, one minimum or one maximum. Let me go in depth now in the optimization problems. Look here. Let me define in a possible cost function. We can see a little bit in abstract way, but the error is between what? Y vector, the measurement, 38 Weber, I don't know, 5 Weber, and so on, no? Minus y hat. Y hat is quite abstract. Again, y hat is the right expression. It's clear, row multiply colon. I didn't repeat it today. Basically, this right expression on the right part of this, let me say, inequality, represent exactly the right part of this. The reason is, if you do row multiply colon, this multiply this, plus this multiply this, and so on, until 1 multiply an, I will obtain this expression here. If you remember, also in high school. This means it's just in a translation, just the use, not the language, but the information is the same. Useful for you, we will see now with MATLAB, because MATLAB can solve in nanoseconds if the problem, the optimization problem, is structured in form of matrix and vector. A structure. No? Otherwise, with this mathematical expression, probably there is also some program. But anyway, here really we can use not only the software, but also we can use also some properties of matrices and so on. I will tell you a little bit later. Now, if the cost function, once repeated, that if the cost function is the error between my measurement and my y hat, which is the vector, more concretely, consisting of this point, this point, this point, and let me go ahead, this point, and this point, but the vector which I don't know exactly must be calculated using this A0, A1, and AN. It's quite abstract. The idea is to find A0, A1, AN in a possible idea, such that this area, this vector, the column vector, is the minimal one. Now, so define the problem. If I try to do with MATLAB Simulink, we will see, but it is easy to see, that the minimum in this sense is exactly what I told you last time in the sense a little bit, the absolute minimum basically does not exist in the sense what I intend. This error is in a linear function. Let me say with respect to theta. This means we have the computer will find in general minus infinite in this sense because it's not in a convex function which we can see exactly in the minimum in the classical form as we did in gymnasium. We can see as the comment at the end, no? In the case M, as I told you, larger than n plus 1, the solution does not exist in the sense it's minus infinite. We can try also at the end with the computer if you want. Because this error is not in a convex function, it's in a monotonic function. This cost function is in a monotonic function. This means, it's a shame, we cannot see until the end of the slide. Let me see. I have to improve a little bit here the slide because we cannot read until the end. Let me see. To be optimized, no? The last sentence is to be optimized. Because the function is in the monotonic one. If you remember in high school, in the monotonic function, defined on all domain, the minimum is minus infinite. But I can think. But if I consider just, for instance, the positive value, in this sense, larger or equal 0, I will find the error, the minimal error to 0, basically the lower bound of my domain. But in this case, the error 0 means I will meet all points. So this situation we don't want to have, because this is an assumption that the measurements tells the measurement tell us the truth, but we are not looking for the truth. We are assuming that the truth doesn't exist, or if exist, they are affected by noise, by the instrumentation, by noise. Here, the sentence is not possible to be read, but is the cost function to be optimized. No, I will improve a little bit in LaTeX. No? Yeah, and exist, it is 0, the minimum, if m equals n plus 1. I will meet all points. But of course, so in this sense, I have to limit, I have to limit in all case, also in this case here, exists is equal 0. If also in this case, if I limit the domain from 0 to plus infinity, in this case, it's 0. But I meet all points. Let me go ahead. Let me analyze when the problem in the sense of optimization make more sense. As I told you before, we need a convexity of the problem. Convexity means local convexity. The best way, I don't want to say the best way, but we have a global convexity, which we have just one minimum. We have a local convexity if you have some minima. In this case, nevertheless, if you remember the lecture of last time, we need some direct method to look for possible minima which can be used in our for possible solution. When we have just one minimum, we say that the problem is strictly convex. The optimization problem is strictly convex. If no, of course, we have at least, I hope, some local minima to be found. Again, when we have a strictly convex problem, and this means a global convex optimization problem, we have just one minimum. And this, of course, the condition is to have a convex function, strictly convex, just with one minimum. And also, let me say here, a regressor in which I can separate what I know with respect to what I don't know. Okay, I think I didn't forget. Again, a necessary condition is to have a convex cost function. Question, when this necessary condition becomes a sufficient one? As I already told you, this concept that I need also the constraints are our regressor, which are basically linear with respect to the parameters. Or parameter, if I have just one, but in general, parameters I would like to consider. And this is related to this concept of separability. I already commented this aspect here, and then you can find again this slide a little bit what I already told you. Yeah, we can see here again what I told you, that this exploration functions or regressor is basically our model to describe the phenomenon, our model to describe the phenomenon. Of course, this is also the key point to maintain the convexity of the, to obtain the convexity of the optimization problem. This means not only in a convex function, but also the constraint should be, as I told you, constraint means this is a constraint. I mean, I would like to I would like to approximate with a polynomial. But if I use another constraint, for instance, a sum of exponential function, okay, in this case, we cannot separate what I know with what I don't know, because here we have something connected with the exponent. If the parameter are also in the exponent, if the parameter also in the exponent of the exponential function, we cannot separate. Of course, if the parameters are related just to the amplitude of exponential function and the exponent are fixed, in this case, yes. I mean, the concept of a separability is a clear concept. Here a little bit the repetition of this in order to obtain a convex optimization problem. Again, on this example here, in a polynomial, we will see later something with different bases, but it's clear. If I have here, excuse me, here instead of a series of polynomial elements, if I have a A0 multiply exponential function up to lambda 1 x, in which lambda 1 is the parameter to be calculated in the sense of optimization, we are not in the case of an optimization problem, a convex optimization problem, because we cannot separate. The linearity of the constraint of the regressor is in a condition. In this sense, we will see in the next lecture how we can attack with the solver. I will present the particle swarm optimization method, this kind of not convex optimization problems. Look, if the optimization problem is defined using a convex function, and in particular here in our case today, this error square, the sum of the error square here, I put it in a complex form, in the matrix complex form. We can see here E transposed, because do you remember E is the vector, column vector, E transposed is the row, E transposed multiply E is the sum of the error square. I don't know if it's visible. Is the sum of the error square, which can be written in this form here. Why that? Because y hat, excuse me, which is the right part of this expression here, is x multiplied theta. Is x multiplied theta. Is an abstract, yeah, in the sense it depends of A0, A1, AN. Yeah. Now, again, I can write the cost function in this form here. Is exactly the same. This expression here is exactly the same as this expression here. A transposed 1 divided 2 A transposed multiply E transposed multiply E is exactly the same. I don't know if it's visible. Which y hat of K represent y hat of x1, x2. It's a little bit, could be also improved, the nomenclature. It is a little bit, I didn't define K exactly, but represent the measurements. I copy from a book. I will skip these calculations because it's quite boring. But believe me, if you are engineer or data science, probably you can look at this mathematical property, these calculations. Basically, they are easy, but boring. I will sketch the idea. The idea is we can see here again why this expression is exactly what I told you until now. This cost function, the concept is depends of theta. Theta is in a vector. It's the vector of the parameter A0, A1, AN. Just formally, just mathematically. Now, if you remember in high school, if the problem is convex, in high school we didn't consider an optimization problem, or not in this sense, but we found the minimum of a convex function. Do you remember? If you know that the minimum, if you know that the convex function, if you know that the function is convex, it is enough to calculate the derivative of this function with respect to the variable. In this sense, the variable is theta. It's complex here. In the sense theta is in a vector. But basically it depends of many parameters, a0, a1, an. Do you remember in Ginnasio, x squared plus 1, find the minimum. This is a function, a convex function. We don't need to calculate the second derivative and so on. Because if you know that the function is convex, it's enough to calculate the derivative with respect to x. Now, here is quite similar. If the problem, optimization problem, is a convex problem, this condition here, which reflect what we learned in Ginnasio, but of course we can see here theta is in a vector, is not a variable, which consists of many parameters, or you can reformulate everything is in a multi variable functions, anyway. But fix the idea. This condition here, excuse me, this condition here is necessary. No, excuse me, normal is necessary, becomes sufficient when we know, you remember Ginnasio, if the function is convex. The derivative, if the function is convex in the sense x squared plus 1, the derivative to 0 states exactly the minimum. We don't need to verify the second derivative and so on. It's quite similar. It's the problem now. Optimization problem is the convex problem. This condition becomes also sufficient. Originally is necessary, no? But also sufficient. In case it's not convex, the problem, we need also to evaluate the second and so on, the derivative. Now here is a little bit more complex because we're speaking about Hessian, but I don't want to go in depth. To do these calculations, in order to calculate analytically with this indirect method, theta, we need to recall some property, which I don't want to recall now, because they are really mathematically boring. But at the end of calculation, which I will skip, but if you are engineer, if you want to go a little bit more in depth, you can, or data science expert, you can look at these calculations. Basically, the calculations are algebraic calculation. But look at this, the solution. At the end, in this case, the reason is, the problem is in the convex one. In this sense, not all convex optimization convex problem, they have an analytical solution. It could be that nevertheless we need a direct method to calculate the solution in the numerical form, but in some cases, this is one of them, we have an analytical solution which can be calculated offline. I mean, this is the solution of this kind of problem characterized by an least square cost function, basically the sum of the error squared, constrained by a regressor in which I can separate what I know with what I don't know. Basically, a linear regressor with respect to theta. A0, A1, An does not appear square root, does not appear in an exponent function. They appear linearly with respect to exploration variable. We can see it's in a linear combination. Because if you look here, no, we can see very well from here. x1 up to n is something which is known. x1 up to n1 is something which is known. The same for x2 up to n, the same for x2 up to n minus known. This means with respect to the parameter to be calculated, the constraints are linear. This is always a viable solution. We say that the solution of the least square in the context which I tried to explain. Of course, if these two conditions are not satisfied, we need a solver because this solution is not viable. We cannot use it. We will see with particle swarm optimization methods. Yeah, geometrically, we can interpret it, I don't know, here's in a 90 degree as a possible approximation in the domain with dimension n+1, which is the number of parameters of a vector, the vector of the measurement, which is included in a space much larger. No? But about this interpretation, probably you heard about that. No? I try to approximate this vector in a reduced dimension. It is the dimension of the parameter, n+1. Basically, the interpretation says that this method states somehow, it's quite abstract, this interpretation, an orthogonal projection of this vector on an hyperplane, which is defined by n+1 dimension if n is the order of the polynomial. But anyway, this is quite abstract, but probably some engineers, some data science students know and a little bit this possible interpretation, therefore I put it here. Now, very important for today, because I would like to go more in depth on the concept of statistical and deterministic error, and in particular, the cost function idea, because the cost function characterize the solution. Look here. Possible figures of merit, but not the unique one. SSE is exactly what we have seen until now. This is least square. In some books, the name is explain sum of squares, least square. Basically, I consider the sum of each error square. Exactly the cost function which I presented until now is exactly this. Least square, or SSE, we can find different notation. What is practically this distance square, even though it's at the beginning unknown, I have to minimize this distance square plus this distance square, blah, 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 plus this distance square, and so on. SSE you can find in some books. Again, explain some more squares, least square. We can say here in a comment, which I copy from a book, but I need a little bit to clarify what I intend. Deterministic error in the sense of prediction error. I mean, is the difference between what I am measuring at each time and my approximating element, which belong to my regressor, why I'm speaking about deterministic? Because somehow here I don't have statistic elements. Why I is the value, which is fixed. Itself is not somehow characterized by a statistical element. It's what I am measuring. What I am measuring. This means this SSE reflects and something which is more deterministic than SSR, this residual sum of square, because this SSR, we can see that the difference is, instead of yi, I am considering y hat, which is a statistical error. I didn't put many information here, but it is the mean value of the yi. This means I have m measurements. Easy, I can build the mean value. y1 plus y2 plus y3 divided m, trivial, the mean value. This means, of course, this SSR is more oriented to a statistical error because I am considering, let me say, the most important, in the sense, the fundamental element of the statistic. The mean value is the first thing which we learned in high school. In this sense, this indicator, this cost function, is a cost function. This, of course, we can say that is more statistically oriented, because we measure the difference between the regressor, which is something which can be considered deterministic, of course, but with respect to hat, the mean value. A little bit here, we can a little bit understand my original question. Here, we can see what I intend. This is the mean value. Here we have this square plus this square, which is basically what I intend with this. I mean, now I would like to be more precise. Here, the statistical error is 0. Why that? Because if this is y hat minus y overline, overline the mean value, probably I called before y overline y hat. Y overline is the mean value. Now, y overline minus y hat is 0. This means this approach, this approximation, minimize SSR. Basically, if this represents the statistical error, we can say that we have a statistical element inside. This is the minimal SSR. We come back on this a little bit later. Here, we have the minimal SSE. Because if SSE also here, no, we can see, is the measure minus the approximation. If they coincide, the sum is 0. We can understand the question of last time. No? Here we have the minimal SSE, 0. Why the minimal? Because it's square. We cannot have a negative minus infinite as before if the function is convex. Is not convex. Here is convex. The minimum is 0, no? For SSE. Here is the minimum 0 for SSR. Let me see a little bit. Yeah, we have these two important characteristics. One oriented to the statistical error, and here oriented to the deterministic error. Of course, they are a little bit, we say so, but sometimes it's mixed because y hat is in both, but we can say it oriented more in any case. That is the difference between my deterministic structure, the regressor, and the mean value, which is in any case in a statistical element of the measurement. Here I will considering each point. This means we are speaking about a deterministic structure in any case, or the more oriented. Please pay attention now because allows to conclude a little bit with interesting insights. Look at this SST. SST, this total sum of squares, so defined yi, the measurement, minus the mean value of the measurement squared, is something proportional to the variance. Is SST is the variance multiply m minus 1. It's the variance of the value. And you remember, roughly speaking, if you don't remember, it does not matter. No? The measurement minus the mean value squared, sum, is something related to the variance. I don't know if you remember. I didn't put here the definition of the variance. I think if I remember well, the variance is SST divided m minus 1. No, with this correction minus 1, you can consider it as m, but I don't want to insist, but probably you remember this. In any case, this SST depends just on the measurements, on the data. It's proportional to the variance. It's the variance multiply m1. I have to answer this important call, and I come back. Let me stop to record. Stop. Yeah, I mean to suspend 1 second because I need to answer, but I come back here. Now, where is? Totally. Just give me a couple minutes. Excuse me for this interruption. I come back in 2 minutes. Yeah, we will see now a little bit more in depth this indicators or the cost function. And then yeah, we conclude in 10 minutes. SST basically is the variance from the data. About the last part of the slide, I already told you what I intend. No? M minus N, we called degree of freedom. We can understand from Gymnasium, I think. No? From Gymnasium, this, in which M is the number of measured points. I mean, is degree of freedom in the sense, you can look at this. Look at this comment here. N is the order of the polynomial. M is the number of the point. We can see that the linear regressor consists of n equal 1. N equal 1. 1 basically we can see here the comment. For m equals n plus 1, all points are met. Therefore, we are considering m larger than n plus 1 in order to obtain exactly what I told you before and the possibility really to optimize. Because otherwise, in this condition here, m equal n plus 1, we meet all points. And in this sense, we cannot speak of the real approximation in this sense, because we are assuming that the measurements they speak the truth. Basically, for v equal 1, for EV equal 1, we are exactly in this case in which we don't have degree of freedom. We don't have degree of freedom. We cannot really, oh, wait, degree of freedom is all 1, in the sense we cannot really think about a real approximation. Why that? Because the coefficients, this is the key point, depends directly on the points. Basically, it's based on the point. I don't know if you remember in high school, this kind of, where is it? This kind of problem here. I can meet these 2 points directly if I have a degree of freedom equal 1. Let me conclude. Yeah, look at this picture here. Here I would like a little bit to improve the slide. I would like to consider probably this slide here at the beginning. SST is equal SSR plus SSE, but this equality is valid, or better to say in this sense is true in a mathematical sense, for infinite number of measurements. This means in this context here is totally not possible to be applied. But assuming that I can apply SST as we defined before, is here the variance equals SSE plus SSR. This is valid for infinite number of measurements. Now, if I apply it always, assuming that it's approximated, here is extremely approximated. If I divided this equation by SST, I will obtain 1 minus SSE divided SST. Why that? Because SST divided SFT, SST is equal 1. SSR, I will call SSR divided SST, I will call R square. This means this expression here, if I divide it by SST, I can do that because SST is no. SST depends just on the value. This expression here can be written in 1, which is SST divided SST, equal minus SSE divided SST, equal SSR divided SST, which I call R squared. Probably the data science student know what is this R squared parameter. We can see here. R squared is SSR divided SST, 1 minus SSE divided SST. This means this R squared, excuse me, is an indicator which sets basically the statistical error normalized by, let me say, the variance, normalized by the variance. Somehow, this indicator says that for us, if you want to minimize this SSR, R squared, for us, it's extremely important to minimize SSR. We can see from here, no? Because R squared is basically SSR. But in this sense, we can see that if I want to let me say to minimize R squared means to minimize SSR because SST is given as a value. But somehow is to, we can see here, to maximize this element here. This means SSR and SSE, they represent a dual sense, but it's clear also from here, no? Because if this is given, to minimize SSR, this is fixed, no? To minimize SSR means to maximize SSE, because we have this constraint, just roughly speaking, no? SST is given. To minimize SSR means to maximize SSE, because this is constant. This is extremely important to understand this SSR and SSE, they are dual somehow. I mean, in this example, it's clear that R squared is equal 1, because in this case, SSE is 0. I told you before. Because Y1 and Y2, they are exactly Y hat x1, Y hat x2. No? This means SSE is 0 in this case here. It's 1, excuse me. SSE is 0, excuse me. R squared, be a little bit tighter, is 1. The maximal value. R squared assume the maximal value. Look here. Here, why is R squared is 0? Yeah, because as I told you before, no, Y overline is equals Y hat x1 is equal Y hat x2. We can see probably a little bit better from here. I don't know. If this is also, this line is also the approximation, huh? in this specific case. This means here we have the minimal deterministic error. But if you have the minimal deterministic error, we have the maximal stochastic error. Here we have the minimal stochastic error, but we have the maximal deterministic error. What is the maximal deterministic error? Is SSE equal SST, when the SSE equals the variance. This means the deterministic is not is the maximal one because it's the maximal variation, so roughly speaking. But we can see also directly from here this concept here. To introduce the topic of next time, why R square is not a good parameter to be optimized. Yeah, because we can demonstrate that R square, with respect to theta, is a monotonic function. Is a monotonic function. We will see a little bit better next week. And then we need an adjustment in order to realize something more convex. Convex function in this sense, such that I can consider a possible minimum. We will see also with the exercise, in MATLAB to find possible minima. And in this context, we can also consider the optimization of n. At this moment, I didn't consider this n is given, but we will see that we can consider also optimization of the order of the polynomial. This means the number of parameters. This can be used for any kind of regressor. Again, to introduce the topic of next week, we will see also with MATLAB that this element here is not convex with respect to the number of parameters, including parameters means with respect to n. This means cannot be used to determine the order, the number of the parameter, because including more and more parameter, we will reduce SSE and we will increase monotonically R square. This means, in any case, cannot be used to optimize the number of parameters, but of course can be used in order to evaluate the level of SSE, in the sense R square, but for given number of parameters. But the problem which we have typically is more complex. Is not only to evaluate SSE for a given number of parameters, it's exactly to determine the number of parameters. In this case, the order of the polynomial, but in general, the number of parameters, because the real problem in the optimization is, of course, let me see here, to evaluate A0, A1, AN, or for another regressor, again, this parameter, but also how many parameters. And with respect to the problem, how many parameters, this R square is not a suitable one, because in a monotonic function, I don't have the demonstration, but we can intuitively understand, including more element. We will see also with MATLAB, but intuitively, we can see also from here. I will go close and to, let me say, the deterministic solution. No? We have the parameter here, just one, the parameter just two. We have 2 points. I will meet both. This means we can see also from here the monotonicity. No, intuitively is not a demonstration. This means R squared could be used in order to evaluate the level of SSE, the level of the deterministic approximation, but cannot be used in the concept of an optimization, a complete optimization, in which I will consider also the number of the parameters. And the number of the parameters is extremely important to determine the family of the regressor. If exponential regressor, trigonometric regressor, I will attack this problem next week, considering some example in MATLAB Simile and concluding with this expression here, which states a minimax problem inside the R square adjusted. I didn't introduce a square adjusted today, and not yet as a modification of R square, in order to obtain a cost function which is not monotonic with respect to the number of parameters. Because the problem of the optimization in our context is more large to evaluate just how fit the problem. It's really an optimization problem in terms of choice of the regressor, and this is related to the number of parameters, because we want to obtain an regressor with the minimal number of parameters, but in the meantime, which fits in the best way, and this we will discuss next time with this minimax problem. Therefore, the cost function should be a particular one. But we have seen that this R square, in particular R square adjust, is in a compromise set together the statistic and the deterministic error. The deterministic error, because came from SST equals SSR plus SSE, in which the data and the regressor are inside, and inside we have the statistic and deterministic error, and these two parameters, SSE and SSR, try to reflect this dual nature of the optimization problem, statistical and deterministic error, trying to separate both, even though totally separable is not. But we associate the deterministic error, let me say, roughly speaking, to the regressor, and we associate the statistic error to the measurements. But totally separated, and they are not, in accordance with the cost function which we can define, which is in a mixed, always in between. Okay. Thank you. We will see next week. We will try to go ahead with the MATLAB exercise and so on, exactly in this context here. Thank you again.
Thank you, Mr. Paolo. Can I ask a question?
1 second.
Yeah,